Hello, everybody. It's Mrs. Pound, and we are starting a new chapter, Chapter 5, on electron arrangement from BJU Chemistry's 5th edition. Today, we're going to be taking a look at Bohr models from Section 5.1. And the objectives today are to explain the significance of emission spectra to the development of the atomic model, describe the Bohr model and how to explain the spectral lines for hydrogen, and explain the limitations of the Bohr model that led scientists to replace it. So, an emission spectrum is the pattern for colored lines that was discovered while analyzing light produced by heated elements. It's also called a line spectrum. So, that's another name for it, line spectrum. And it looks like this. This is the emission spectrum for hydrogen. And a really cool thing is that each element has its own unique emission spectrum. So we can identify elements by their spectra. And in fact, helium was discovered from its spectrum from the sun before we even discovered the element itself. We knew that there was another element there because we had the spectrum. So, just kind of an interesting fact. Now, the Bohr model is a model of atoms proposed by Niels Bohr in which electrons move around the nucleus in well-defined orbits. Each orbit represents a specific energy level for electrons. This is sometimes called the planetary model, and he envisioned these. You can kind of see this in the background. He envisioned the electrons as going around like a fixed track. Now, this is a three-dimensional track. Um, these are the principal energy levels. These are the orbits of energy levels in the atomic model. They're like little tracks, but they're three-dimensional. They're more like shells that you peel away. Okay, kind of like think of an onion. Okay, each layer that you peel away would be a different principal energy level. So it would be going around three-dimensionally around the nucleus of the atom. These are also called energy shells. Now, these energy levels are quantized. So, energy emission comes in certain quantities. So, let me explain this. This is kind of like a ladder. Um, the electrons can be excited. So, they can go, say, from energy level 1 up to energy level 3 if it gets some energy. So, how would we energize it? We could add electricity. We could add heat. We can put it in a flame, which we're going to do in class. Um, to add energy to excite the electrons to have them move up to a different energy level. Now, you have to have enough energy for it to fully jump up to the next level or the third or whatever level it's going to jump to. It can't go halfway. That's what it means by the fact that it is quantized. There's no halfway in between the energy levels. It's either on a level or it's not on a level, kind of like a rung of a ladder. As you go up a ladder, you must go to the next rung or you're going to fall off. There's just no halfway in there. They are at certain heights, they are quantized, okay? And so, just like a ladder, the higher you go, and then if you fall off and go down, the more energy is going to be released when you hit the bottom. So, if you fall off the bottom rung, you're not going to do too much damage, right? Not a lot of energy there. But if you're on, say, the 10th rung of the ladder and you fall off, you could probably break a bone, okay? Because a lot more energy is released. And it works that way with the atoms too. And this is what Bohr recognized that as they jumped up and fell down, there were different quantities of energy released, and these were shown, as we saw in the line spectrum, with different colors. So the more energy released, the more towards the blue purple end of the spectrum. The less energy released, the closer to the red area of the spectrum. And so, but there are those lines on there, and they always happen at the same point. So that's why it is quantized. You didn't see the whole color of the rainbow coming out. It was just in certain spots. And that was corresponds to these different energy levels that the electrons are falling down from. So the electrons are usually in the ground state. This is the lowest energy level of electron in the Bohr model. So right now, these are in the ground state. No energy has been added, no heat, no electricity, anything like that. And the highest number of energy levels that an atom can have at ground state, its lowest energy state is 7. And if you look at your periodic table, you will notice that off to the left-hand side, there are 7 periods. These correspond to the different energy levels. So our periodic table is really um, organized based on atomic theory. Okay, so you'll notice if you get out your periodic table, those numbers off to the side. Now, they can be excited, as I said before. This is any energy state other than the ground state resulting from an electron absorbing energy. So they're in the ground state, they absorb energy, they become excited, they fall down, they release a certain amount of energy that is quantized that we can see in that spectrum every single time. So Bohr's model helped to explain the emission spectrum of the hydrogen atom. Bohr found that the frequency of the spectral lines in the hydrogen atom can be predicted by the presence of colored lines in an emission spectrum. He related um, this to those lines. Bohr also found that atoms had specific energy levels and that excited electrons can jump up to a higher energy level and they fall back to their original energy level, releasing that energy that we see in the spectrum at certain points. The problem. The model accurately described only the emission spectra of atoms with one electron. It only worked with hydrogen. It didn't work with anything else. So scientists needed to come up with a more workable model that explained atoms with more than one electron. But it was a start. And it's a workable model that we use today to explain different things. Not as good as some of the other models, but you see it a lot, and we do use the Bohr model to represent where we put the electrons in atoms. So our objectives today were to explain the significance of emission spectra to the development of the atomic model, describe the Bohr model and how it explained the spectral lines for hydrogen, and explain the limitations of the Bohr model that led scientists to replace it. So don't forget your 5 questions in your notes, and I'll be back with another video.